This is Alexander Müller-Hermes from the University of Oslo. 2015 from the Technical University of Munich. Yeah, so it's my pleasure to introduce Alexander. We'll talk on fault-tolerant coding for quantum.
So I hope you can all hear me. Yeah, I think it's fine. Yeah, thank you so much for inviting me. So it has been very nice so far, and yeah, I mean from the program, and yeah, I'm sure it will be continue to be very nice. So indeed, I want to tell you about this recent work of mine, which is actually joint work with Matthias Christande, and we have a follow-up with Paula Belzig on this. It's about a fault-tolerant coding for quantum communication. And since I've been told this is a rather mixed audience, I want to be very very pedestrian on this, and please interrupt me if anything is unclear. So at least I think in the first part it should be hopefully clear for everyone. Okay, so my outline is that I will start by defining what a capacity is. So whenever I say quantum communication, I mean this in this Shannon theoretic sense, so that we have like some Shannon theoretic problem, and the central notion there is that of a capacity. Then in the second part, I want to tell you about quantum communication and noise. So how can noise affect quantum communication processes? And in the final part, I want to talk about communication between quantum computers, which is what this work is about. Okay, so let's start with a really pedestrian introduction of what a capacity is. Get the cursor here out of the way. So capacities quantify how much information you can send over noisy quantum channels or noisy channels in general. And this idea goes back to Claude Shannon from the 40s. And so maybe the first question is, what is the communication channel? And here, to quote Shannon, the channel is merely the medium used to transmit a signal from transmitter to receiver, and it may be a pair of wires, a coaxial cable, a band of radio frequencies, or a beam of light, etc. Of course, when Shannon wrote this, what he had in mind was classical channels. So he really thought of the channels that where he sent a classical symbol over a wire. So when he talked about the beam of light, I'm not sure he considered the quantum degrees of freedom of this. So now quantum Shannon theory takes these ideas of Shannon and takes it to the quantum setting. So let me now mathematically define what I understand what a communication channel is. So for Shannon, and I hope you can all read this, we have this classical case for Shannon. So there you have an input alphabet sigma A and an output alphabet sigma B. And the channel, as I want to define it now, is just a map from this input alphabet to probability distributions over the output alphabet. So think of some kind of noisy telephone wire. And when you send like your bit over this noisy telephone wire, you say 1 or 2, it will get a bit scrambled, and maybe what you receive at the output is maybe 1 with probability something, and 0 with the opposite probability. Quantumly, we understand like a quantum channel is a completely positive and trace preserving map. So I will not define these terms because isn't super important for this talk what this precisely is, but it's just like a general quantum process that takes some input to the output. Here I should say that in all of this business, it's somehow, in the way I use it here, there's some kind of Markovianity assumption hidden here. So I will always consider this channel somehow with kind of a Markov process. So this classical channel you can understand as a classical Markov process, and this quantum channel is a quantum Markov process. This is not strictly necessary for this, but here let's keep it here like this. Okay, So for this channels, so let me give you an example of the most easy classical channel that you could envision, which is this binary symmetric channel with a parameter p, describing the probability of this bit flip. And as I described before, that you want to send 0 or 1, and with probability p, your bit is flipped to the opposite value, and with 1 minus p, it stays the same. Okay, so if you have this kind of channel, and maybe you have this telephone wire that's a bit noisy, how do you communicate information over this? So what people consider, or what Shannon considered, were kind of coding schemes that look like this. So at the sending end, the sender would take a message and encode it into some more words in this input alphabet to the channel. And usually these words are longer than your message, so it adds some redundancy here. Then you would send this over the channel. You would apply the channel many times to send this, this word over. And at the receiving side, the receiver could apply a decoder to get some approximation to the message. And usually this is not perfect. Usually there will be some error epsilon here, some probability of error. The goal of Shannon theory is to maximize this rate of communication. So I want to maximize the number of bits that I can send. So this will be the logarithm base 2 of the number of messages that I want to send over the number of uses of the channel. So I want to maximize bits sent per channel use. And I want to do this while I minimize the communication error. Okay. For this discussion, it's not important at all whether this is a quantum channel or classical channel. It's just, I can envision this as a classical channel, then this encoder will make a classical code word, or I can envision this as a quantum channel, then the encoder will produce a quantum state. So it's somehow really a general definition that you can modify as you want. So Shannon studied these coding schemes, but what he wanted to quantify was, what are good coding schemes and what are bad ones? So let me give you 2 examples here. Maybe the easiest example is that of a k repetition code, where you want to send 2 messages, so a single bit, so 0 or 1, and your encoding is just to take the bit and repeat it k times. Then if this binary symmetric channel, say, has a small probability of flipping the bit, then you can see that at the receiving end, if you send this word, many of the bits will remain unflipped. So if you do a majority vote on the bits, you just count which bit appears most, you will be able to decode this with high probability. So the rate of this is, so logarithm of 2 is 1, so it's 1 over k, where you use, because you use the channel k times, right, to send these words of length k. And you can convince yourself that the error goes to 0 as k goes to infinity, if this probability of bit flip is maybe less than 1/2. Okay. That's one coding scheme. Another more clever coding scheme is the 4-7 Hamming code that takes 16 messages, so 4 bits of information, and encodes it in 7 bits of information. And it does this rather cleverly. So what you do is you write the bits into this diagram of intersecting circles, so B1, B2, B3, B4, and then you choose the 3 other bits to make the parity in each of the circles even. And if you do this, you get code words that belong to this Hamming code. For the decoding, if you now envision some bit is flipped here, then I can look at which circles have odd parity. And I can, for example, if this circle and that circle have odd parity, then I will flip the bit B1 back to restore the even parity condition. That would be the most likely event of an error, right? That is what the decoder would do. If all 3 circles have odd parity, I would take the bit B3, right? So this code corrects any single bit error that you can convince yourself of, has a rate of 4 sevens, because you send 4 bits over 7 bits of code words of length 7. And the error scales somehow like p squared for this binary symmetric channel. So there's a constant in front of this that I don't want to talk about, but so if your p is small enough, then this will be lower than p. So which of the 2 codes is better? It's difficult to say. So what you could do is you could plot these codes into this error rate plot. And this you should really see as a qualitative plot, so don't nail me down on the numbers here. But so how it would look like is that you have these repetition codes maybe, and there are a family of them, that go to this to zero error, right? Because the error in the limit goes to zero, but the rate also goes to zero. You have the Hamming code, that's a single point here. There are other Hamming codes that would give you other points here. And there's this one point that's the trivial code, where you just send the bit unprotected, that has an error probability of p, okay? And you would see that there, if you would plot more and more codes, you would see that there's this line where on the right side, you will not find any codes. On the right side, you have no coding scheme that lands in this region. Where this line intersects this lower axis, that's the capacity of the channel. So you can think of this as the maximum or the supremum of asymptotically achievable rates. So there might not be a code that sits in this point, but at least there's a sequence of codes that approaches this point. And that's what the capacity means. So let me formulate this a bit more formal. So more formally, as I said, the capacity is a supremum of asymptotically achievable rates. And by this I mean that there exists a sequence of coding schemes with rates Rn and errors epsilon n, such that Rn converges to R and epsilon n converges to 0. Okay. So this is like the definition of the capacity. And again, the definition is the same for the quantum channels or classical channels. Okay. So when Shannon wrote this paper in 1948, he actually also solved this problem of computing these capacities. So what he did is that he realized that if you take a random encoder in a certain sense, then you can find these asymptotically, this sequence of coding schemes achieving the capacity. And that's his famous capacity theorem. So for any classical channel, the capacity is given by this kind of this formula. There's a supremum over an entropic quantity, which is called the mutual information, which is given by the Shannon entropy of some probability distributions related to the joint probability distribution of the input of the channels and their outputs. It's not super important what this is exactly, but I want to emphasize here that this capacity formula is something that you can compute. So this is like it's a nonlinear function, but it's not a complicated function. And indeed, you can compute this for channels for channels of interest. I should also say, right, this only involves the channel itself in this distribution here, this joint probability distribution of input and outputs, and not higher copies of the channel. Okay, so this is a classical case. And the fact that this is a nice formula, this does not go through in the quantum case. So in the quantum case, you can use entanglement to construct coding schemes, and that makes life much, much harder. Or more interesting, if you want to put it like this. So the coding schemes achieving the classical capacity of a quantum channel look like this. So you take a message, and you prepare a large quantum state that is entangled in these blocks. So you have blocks of some length, k, say, and you prepare a quantum state that has entanglement in these blocks, and in general it's highly entangled. Then you send all of this over the channels, and in the end you apply a global measurement. And this should be close to the message. These are the coding schemes that achieve the classical capacity of a quantum channel, and you see that they use entanglement. Yeah, at least I draw it like this. So the analog of Shannon theorem is this Holevo-Schumacher-Westmoreland theorem that shows that the classical capacity of a quantum channel is given in this way. So it's also an entropic quantity, where this H here is the von Neumann entropy of this quantum state. But this time, this entropic quantity involves T tensor K. So it involves K copies of the channel. And it regularizes, so it divides by K and takes the limit of K going to infinity. And this is not like an artifact here of some kind of proof or anything. This regularization is really needed here, as Hastings showed in 2008. And this signifies, this regularization, that this entanglement here actually helps you communicate at higher rates. So when you want to communicate at high rates over a quantum channel, you want to be able to prepare entangled states. Okay. So the takeaway from this first part is that coding schemes achieving rates close to the capacity of a quantum channel are pretty complicated operations. So they need entanglement and they need global measurements. It's not something that you can just easily do if you want to get close to capacity. Okay, let's now discuss quantum communication and noise. Or are there any questions regarding this? Okay. So, quantum communication and noise, I want to consider two types of noise here that could affect the coding scheme like this. The first type is noise affecting the communication channel itself. The second type is noise affecting the coding operations. And now you might wonder, right? Because how I sold this to you before is that this communication channel, this somehow captures all the noise that this wire experiences. And this is true, but there might be more noise in certain scenarios. So this is why this noise is usually studied in an adversarial scenario where you have a third party, a jammer, that tries to jam the communication between Alice and Bob, between the two parties. So this jammer might have the possibility of altering the channel and make it worse or try to do something funny to make it difficult for the two parties to communicate. And indeed, this scenario has been studied a lot in this setting, both in classical information theory and recently in quantum information theory. The second type of noise is this noise affecting the coding operations. And this is more easily, I guess, to motivate because your devices might be unreliable. So although it's more easy to motivate, this has not been studied so much in classical information theory, because guess what? These computers, they work pretty well, right? So classically, we don't have this problem that much, I would say. But quantumly, of course, if we want to use quantum computers here, somehow this is a problem, because quantum computers, as we know, are actually quite noisy. So now I should say that when I now have this coding scheme, in this final communication error, I should take into account this noise. And in principle, this would depend on the noise process, what will come out of this. Okay, so let me look at this first type of noise first, the one that affects the coding, the quantum channel. And I want to consider three types of this noise, or three models that people have studied. First one is called compound channels. The second one is arbitrarily varying channels, and the third one is what we made up, is channels under arbitrarily varying perturbation. So let's start with the compound channels, which is very nicely to motivate. So for this, you fix some family of channels. This can be in principle an uncountable family of channels, so it's really like a large set of channels. And instead of applying the channel T that you know to every of the wires, you apply some channel from this family on each of the wires. And okay, so if we do this, then you can ask the question that if you now use encoding and decoding, so if you use a coding scheme and you apply this channel T nu, at what rates can it send information? So here, this error now depends on the nu, so it depends on the channel that I use. Note here that I will choose the coding operations, and then I will choose the nu, right? So that's a setting that I'm interested in. So I want to maximize the rate of communication again, but now I want to minimize the worst case error. So my coding operations, they should work for all nu that I could think of. So I take epsilon, the final coding error, the worst case error, to be the maximum of these in nu, or the supremum, if you take an uncountable set. Okay, so at what rates of communication are possible? And Oh, yeah. So one maybe channel of particular interest for this talk is this compound channel where all the channels in the set are delta close to the communication channel that you're interested in. So that would correspond to a scenario where you only know your channel approximately, which is somehow, yeah, a relevant scenario if you want to communicate over these noisy telephone wires, maybe. Okay, so this is the theorem, and this has been proven by Datta and Dorlas for like finite sets, and by Bielakovic and Boche for arbitrary sets. And it looks a bit similar to the classical, to the Hollywood-Schumacher-Westmoreland theorem, actually very similar. So the capacity of the compound channel, so the supremum of asymptotically achievable rates, is given again as a regularization over an entropic quantity. But this time, it's an entropic quantity contains an infimum over nu. So somehow you take the entropic quantity that is worst over all the channels, T nu from their family, and then you do some optimization and take the regularization afterwards. So if you have this channel here, this compound channel that I just described, where all the channels are close to T, delta close to T, you can use continuity of these entropic quantities to show that the capacity for this particular compound channel will be larger than the classical capacity of T minus some function in delta that goes to 0 as delta goes to 0. And I should point out that this is stronger than continuity of the capacity itself. So you might know that the capacity itself is continuous in the channel, but that doesn't tell you about the coding schemes. So just because the capacities are close, it doesn't necessarily mean that you can use the same coding scheme for both channels. This here shows that there's one coding scheme that works for all of these channels simultaneously, in the sense that it achieves 0 error in the limit. So the error is not bounded by delta or anything. It's really 0 error in the limit for all of these channels. That's somehow the problem. Yep. In what? Yeah. Yeah, true. Yeah, exactly. So this is a nice result if you are interested in this, if you don't know your channel exactly. Okay, so while this is a nice setting, these compound channels, they are not very quantum in a sense, right? Because you still have like tensor power, like you still have these IID copies. You don't have entanglement between the wires. So maybe your jammer puts in some entanglement between the wires in some sense. Maybe it connects the wires with some machine and then does some funny business. So this is where these arbitrarily varying channels come in. So these are channels that are affected by a common environment. So now, instead of a channel T that has a single input and a single output, I take a channel T that has 2 input systems. One, which is like under control by the communicating party Alice, and the other one that's under control by the maybe adversarial party Eve. So it's a channel, so it has 2 inputs and 1 output. And all the inputs of the channels, they get some environment state sigma. So I hope you can read this here, this blue. This environment state, it might be highly entangled between these number of copies. So it can induce like correlations between the channels, quantum correlations between the channels. So and this is a pretty, pretty nasty channel model. So there are some nice results. So under certain circumstances, you can reduce this to the compound channels that I showed before. You can use some symmetrization technique, some or post-selection techniques to reduce this to the compound channels from before. But in general, you don't know much about this. So, okay. So this is, I just want to mention this, that this is something that was studied before, actually also quite recently. So we will need a variation of the arbitrarily varying channels. Yep. Sorry? So what's the relationship between the 2 pictures? It's just I replaced this IID scenario by this. Oh, very good. Yes. So I mean, in principle, you can have, yeah. You have to specify this channel somehow to know the answer to this. But so what you could, for instance, do is you could put in an IID environment or like a tensor power of some fixed states, sigma tensor K, for example. Then you would recover a compound channel. And if you had like separable states, you would also get nicer channel models here. But in general, it might be very complicated. Yeah. Yep.
Is it allowed to allow
No.
Or do you always assume that the encoder can? Like here, I mean, like the use case here is when you entangle all of the different channels, right?
Yep.
But E, like.
Yes, I think.
Several to the input that the encoder should.
Yes, so this is always like this gemma comes in when the transmission happens, right? So the Alice is still able to prepare a state in her lab that she wants to send. Yeah. That's not correlated to Eve. Yeah. Okay. More questions? As I said, for this, what I want to talk in the final part, I will need a variation of this arbitrarily varying channels. And here, I want to basically combine the two ideas that we had before. So we have this channels that are somehow close to T, but I don't know which channel it is. And, and I have this arbitrarily varying idea. So these are what I call channels under arbitrarily varying perturbation, or AVP. So the channels are affected by a common environment, so they are an arbitrarily varying channel, but they only are affected weakly. So that's why I call this a perturbation. So what I mean by this is that I replace this channel T by the following arbitrarily varying channel, where with 1 minus delta probability, I do T tensor a trace on this system that Eve controls, plus delta some arbitrarily varying channel. I should say some, yeah, arbitrarily varying channel. So, yeah. So you should think of delta as being small. So this is really the scenario that you, with high probability, you will just do the channel and you will ignore Eve's attempt to alter this. But with some small probability delta, you will, yeah, Eve can alter this a bit. Yeah. No, they are like some quant, like there are some.
So they don't necessarily unitary.
Sorry, so I'm not sure. Yeah, so they are like, I mean, you can think of them as like unitaries where you maybe trace out some systems, right? So they can be dilated to unitaries, in a sense. But
it's two problems, right? One unitary, and second is the fact that you don't know what they are.
Yes, exactly. Yeah. Mm-hmm. So, okay, more questions? So, yeah, think of this delta as being small. So it's really like with high probability you do the channel that you intended, and with small probability you do this, get this environment effect. Get the no, it's still not unitary. You get a yeah. Mm-hmm. So I should also emphasize that in this business now, when we talk about capacities for these channels, so it's maybe here. So if we now look at the coding schemes, let me say this first. So if you take these coding schemes now, right? I again want to take the epsilon now will depend on sigma, the environment state, on delta, the strength of this perturbation, and the channel n that I can choose here. And I want to maximize the rate again, and I want to minimize again the worst case error, where I now take the supremum over all of these quantities, but I keep delta fixed. So I want to keep delta fixed, but I want to take the supremum over the environment state and this channel n. And I can even take, for what follows, I can even take the supremum over the dimension of the environment. So even this is not constrained. So it's really like you can do much more than in the usual arbitrarily varying channel scenario. Okay, I should also emphasize that when you now talk about capacities, so capacities again are the supremum of asymptotically achievable rates. I want to get the error down to 0. It's not so difficult maybe to see that you can code with an error that is somehow a function in delta. But you want to get the error down to 0. You don't want to have it bounded by delta. Yeah. Okay, so this is our result. In a nutshell, so in a very high level picture, that for each k, this capacity that you get, where keep delta as a parameter and t, so delta again is this perturbation strength, this is larger than 1 over k, this quantity that appeared in the Rolevaux-Schumacher-Westmoreland theorem, minus a function in delta and k that goes to 0 as delta goes to infinity, it goes to 0. So when you choose delta small, you can get these quantities. I should say that this function is in a way, it depends on k in a way that you cannot take the limit to k in k going to infinity here directly. So then this bound would vanish. And we actually don't know whether this is an artifact of our method. So just saying this is an open problem whether you can get rid of this, this k dependence here. So anyway, since this quantities converge to the classical capacity as k goes to infinity, you still get this result, that if delta is small enough, and it doesn't have to be 0, I mean, there's a finite delta that you can choose such that this arbitrary varying perturbation capacity is close as a function of delta to the original capacity. I mean, I know precisely, like, you can use this function, right, to compute this, how fast this goes, but it's probably far from optimal. So, okay, so these are these arbitrary varying perturbation capacities. And what I want to take you, so you should remember from this that you actually can get close to the capacity here with these arbitrary varying perturbation capacities. So the takeaway from part 2 is that in quantum channel theory, we can deal with many different channel models beyond the standard ones. I want to emphasize that these are very non-standard channel models. And the capacities are actually quite robust against additional noise. This will be important in the final part. Okay. So now, let's talk about communication between quantum computers. So what are the challenges here? So if I take now, I want to do all these coding schemes, right? Someone tells me a coding scheme and asks me to build a device that does it, right? Then I have two challenges. First, I want to prepare a state that is highly entangled between these different wires. And also, on the decoding side, I need to perform quite complicated measurements. So this is not possible to just set this up like without thinking. So what you actually need to do this, so you need to execute complicated quantum circuits, and the only way we know to do this is to use a quantum computer. Correct me if I'm wrong on this, but I think this is gospel. I don't know. So when you do this on a quantum computer, you would have some encoding circuit and some decoding circuit that I can choose such that I approximate any coding scheme that I come up with on my piece of paper. And this coding scheme, these circuits I execute on my quantum computer. But of course, quantum computers, they experience high levels of noise, as for now at least. So there will be some noise process hitting these circuits. And somehow my coding scheme should be able to deal with this. So if I don't consider a communication scenario, if I only consider a quantum circuit, we know how to do this, right? We know that we have this whole theory of fault tolerance that we can use to protect a quantum circuit. Let me quickly review some techniques here. So the idea, if you just have a circuit that you want to execute on a noisy quantum computer, is to run the circuit instead of running it on noisy physical qubits, you want to run it on less noisy logical qubits. So for example, you could take a logical qubit, this is a 7-qubit Steane code, you can put a logical qubit into a subspace of 7 physical qubits like this, so some complicated state representing the logical 0. The logical 1 is like x tensor 7 applied to this logical 0. And this gives a way of encoding a qubit into these 7 physical qubits. Let me emphasize here that unlike channel codes, so I mean, I now talked about channel codes for quite some time, now I'm talking about computational codes, right? And for these computational codes, you want to have more structure. So for the channel codes, I can at least mathematically get away with giving you a random code, and you might not, I mean, if you're an experimentalist, you might still complain a lot, but as a theorist, I think you would not complain much. But for these computational codes, you want to have more structure in order to prove the theorem that you want to prove even. So for example, you might want to have some transversal gates or some gates that you can apply like easily on the code space. You want to have an efficient error correction and many more things. When you have this code, right, you could, there's a nice construction by which you can get better codes, which is called concatenation. This was now actually you cannot read this, but okay. So here sets level 0. So on level 0, you take the physical qubits and you group them in, if you now use the 7-qubit Steane code for this, then you group them into groups of 7 qubits each, and you encode them to get like level 1 logical qubits, say 7 of them. And then you do this again. You do you encode the 7 logical qubits into 1 logical qubits of a higher level, so level 2. So by this you can make these levels for each natural number of higher and higher protected error correcting codes. And this is often used in fault tolerance because it's not easy to prove theorems using this construction. It's not necessarily the best code that you want to use in experiments, but for theory it's nice because you have this kind of nice concatenation structure. So there's now this nice result, which is called the threshold theorem, which now supposes that if you want to execute your quantum circuit on logical qubits, then you replace each gate by a corresponding gadget. There's a kind of a prescribed way that you have to fix some gadgets that implement your gates on the code space. I want to write gamma subscript C here for the implementation of a circuit in this code C. And then there's this result by Aharonov and Ben Orr, and maybe the one that I'm using here should be attributed to Aliferes, Gottesman, and Preskel, that there's a family of codes which is given by the, in this case here, by the concatenated 7-qubit Steane codes. And there's a number, P0, that is called the threshold, that is not 0, but it's between 0 and 1, it's not 0, such that if you take this encoded circuit with faults of strength P, whatever this means for now, then this is epsilon close to the ideal circuit, where epsilon is a small number, or you can make it very small by taking L, the level of this code, the level of the concatenation, to infinity, whenever the strength P of the noise is less than the threshold. That's kind of a high-level description of the threshold theorem. What I put under the rug here is the noise model that I allow here. And there are different noise models that you could study where the theorem holds. And okay, I will put this under the rug for now. Maybe ask me later if you want to have details. So this is a theorem. Let's apply this to the communication scenario. So here, how would it look like? So I have this encoding circuit and I implement it in the code C. And I take the decoding circuit and implement it in the code maybe C prime, but okay, let's maybe take the same code here for the rest of the talk. Now I have the circuit executed on the logical qubits. But my information carrying system is still the noisy telephone wire that I started with, or the noisy fiber optic cable. So this has not changed. So now there's a mismatch between the systems doing the computing and the systems doing the information transmission. Do you see this? I mean, I could, if each of these wires, say there's only like the 7-qubit Steane code, then each of these wires would contain 7 qubits. And the information would sit in the logical space of these 7 qubits. I could take more channels here, but then I should take this into account when I compute the rates. So that would fuck up my rates. So here, there's a mismatch. How do I solve this? And I don't want to claim that this is the only solution. There might be other solutions for this. But how we solved it was to use interfaces. And interfaces, I mean some quantum circuits that take the logical space down to the physical space that my information carrying system uses. And of course, you might need to use this anyway if this is a different kind of underlying physical system than the information carrying system. But, yeah. So I don't want to go too much into details of what these interfaces are. You could choose many different circuits here. For the concatenated codes, there's a particular nice one. I will tell you the properties in a moment that I need for this, but let's keep this for now. No, that's the crucial thing. So they are quantum circuits, so they should experience noise. So in this picture now, it would be really nice if I could compute, instead of computing the channel T, I want to somehow take the interfaces maybe to the channel side. And this is what we call the effective communication channel. This is a channel that, so what I want to do now in the rest of the next maybe the last 5 minutes or so, to transform this whole picture in a way that I can compute this effective communication channel. And this will be the channel that acts on the logical qubits, on the logical space. So when I want to design my encoding and my decoding circuits, instead of coding for the channel T, I should really code for this effective channel. That's somehow the take-home message. But let's see how this looks like. For this, we need to understand how to analyze noisy quantum circuits protected by an error-correcting code. And this is a bit technical, but let's go through it like slowly. I don't know how to explain it better. So if you take this kind of 7-qubit Steane code as a concrete example, then this, as you might know, it's a stabilizer code. So this is a common eigenspace of 6 commuting product Pauli operators. And the common eigenspace corresponding to the +1, +1, +1 eigenvalues. For any string S there are 6 zeros or ones, so 6-bit string, I can consider the other eigenspaces corresponding to other to these other 6 eigenvalues. So I can consider the common eigenspace of these stabilizer generators corresponding to eigenvalues -1 to the S1, -1 to the S2, -1 to the S6. That gives me like 2 to the 6 spaces, WS, and they are the spaces of vectors that you would consider, that you would call the vectors with a syndrome S. So if you know this, then you might know that you measure these kind of observables to determine the syndrome of a vector when you do error correction with this code. I don't want to measure here. I want to really just look at this algebraic structure for a moment. So I have these eigenspaces, and they have some nice properties. So because, first of all, like the W corresponding to the 0 string, all 0 string, this is the code space, right? This is the common eigenspace to the +1, +1, +1, +1 eigenvalues. When I have different strings, then these spaces, they are orthogonal. And so I can essentially do a dimension counting argument now to see that the whole space of the 7 qubits is a direct sum of these spaces WS. Or to put it a bit differently, I can relate these spaces WS to my code space by fixing some product Pauli operator. This is not unique. There's some choice here, and uncorrectable errors actually, they come into the picture by this choice not matching up the actual error that happens. But yeah, that's important now. So you can write these spaces as some chosen product Pauli operator ES applied to the code space. And then you can define a basis for the whole space by these words, so by these vectors ES applied to logical states in the code. So if you've never seen this before, it might be a bit fast now, but it will get better in like two slides. Yeah. It's technical, but I don't know how to say it better. So when you have this basis here, I can define a basis change, a unitary change of basis that takes each of these basis vectors, E as applied to the logical state B, so it's logical 0 or logical 1, and I transform this to a product basis. So where I take the logical state in the first part and this syndrome state in the last part. And with this, I can define two quantum channels that are what I call the ideal decoder and the ideal encoder. And they are really like analytical tools to study these noisy quantum circuits. They're inverses to each other, and this ideal decoder separates somehow data from noise. So if you view this as a noisy quantum state, then it gives you the data, tensor, and noise part. And now I don't think that there's much time to go into more details of this. Talk to me later if you want to know more about this. Because I think so this is implicit in Aliferes, Gottesman's, and Prescott's paper, but I don't think it's very much used in the quantum fault-tolerant community. And I would like to hear, maybe if there are people working on fault tolerance, I would like to hear their opinion on this. Yeah. So these two operations are fixed. And now I can somehow express the way the threshold theorem works is by using these operations, so now similar operations for the concatenated Steane code, to transform noisy quantum circuits. That's how Aliferes, Gottesman, and Prescott proved their threshold theorem. So in particular, it looks like this, that if I have a circuit that has classical input, and I'm now putting a lot of some technical assumptions under the rug here, then if you apply this ideal decoder to the output wires, then this will be with large probability. This epsilon L is the probability that appeared in the threshold theorem, so it will be small. So with, so with low error probability, it will transform to the ideal circuit and a state sigma encoding this fault pattern. And I could envision, like, so this is now maybe where my mathematician sense comes in. You can envision here really like arbitrary states. So they are not necessarily classical. They can be entangled between this here. This has to do with the way that these encoders and decoders are built. So the state here decodes a very complicated fault pattern that acts on the circuit, but it separates this from what's actually happening. And yeah, this is with high probability. So this is the case where these errors are correctable. So if you have a quantum circuit that has a classical output, you can somehow do the similar thing. You can, essentially, when you end with measurements, you can introduce decoders after the measurements, pull them through the circuit, transform it in this way, where you get the ideal circuit acting on the data wires of these decoders, of these ideal decoders, and you get a partial trace on these other wires. That's how the threshold theorem looks under the hood somehow. So if I use this in the communication scenario, I can compute the effective channel. So what I do is I do this. It's very complicated now, but it's actually not very complicated, but it's maybe a bit of large picture. So what I do is I introduce the decoder, the ideal decoder and encoder here, which is, I'm using that they are mutual inverses, so I can introduce an identity here. And, oops, okay. And then I can use this threshold theorem that I just had on the previous slide to transform this first part to the ideal encoding circuit states and the state sigma encoding the fault pattern here. So I can also transform the decoding circuit using the other part that I had before. And I have this effective channel now here. I can now use this is the effective channel that emerged here, right? This small part here. And now I use a fact that for this concatenated code, there are interfaces that actually work pretty well. So when you go down from a logical space to a physical space, and you have a gate error probability of P, then this interface cannot be better than probability P. Like the failure probability P, you cannot go below failure probability P because there might be an error happening in the last gate that you execute here. So it's rather remarkable that for the concatenated codes, you can build interfaces that get an error probability of C times P for some constant C. This you use, so these are interfaces now that have this property that they are ideal identities with probability 1 minus Cp, where C is like some constant, and P is the strength of the noise. And if you introduce this, then you see that your channel in the end is actually an arbitrary variant perturbation of P. So with 1 minus Cp probability, this interface will function as intended, and your channel just it corrects all the errors into making this partial trace. And you get your channel that you wanted to. And with the opposite probability, you get something else that depends on this faulty interface and how it interacts with this environment. So now in this picture, this whole coding scheme now transforms to this coding scheme under arbitrary variant perturbation that we know how to treat. So by what I told you before. So this is a final theorem that we have, that if you now define a capacity that takes into account these noise affecting quantum circuits, then for every epsilon, every channel T, there exists a threshold such that if your, okay, this is missing now, if your error strength is below this threshold, you get close to capacity, or you get larger than capacity minus epsilon. Note that this threshold depends on T, and we don't know whether there's a uniform threshold that doesn't depend on T here. Okay, so the takeaway of this part 3 is that noisy coding schemes for classic communication are equivalent to coding schemes with an arbitrary varying effective channel, and to transmit information reliably, you should use your coding operations tailored to this effective channel. Finally, some open questions. So we don't know really for which circuit codes this works. So it works for concatenated codes, but for more realistic codes, we don't really know. Also, what are these states appearing in the environment? This depends on your fault model and on the circuits that you execute. And I'm not sure that there's like a good understanding of this. And finally, you can ask how to do this in other settings. And now we have a follow-up with Belzig and Christandl on entanglement-assisted capacities. And you could do this in other settings as well. And with this, I want to thank you for your attention.